the statement of Schur's lemma is as follows. So if we have two irreducible finite dimensional G modules V and W, and if there's a G intertwiner between them, so if let's write it here, T is in Hom G V to W, so if T is a G intertwiner between V and W going from V to W, then, and then there's three properties, so either T is an isomorphism, because remember, just because T is a G intertwiner, it doesn't automatically mean that it's a isomorphism, it's only a homomorphism at that point, or T is zero, the zero homomorphism, or the zero map. So the second property is if V equals W, so if T is an endomorphism, then T equals lambda times the identity map from V to V for some lambda in the complex numbers. And then the final property is the dimension of the space of intertwiners between V and W is 1 if V is isomorphic to W, and 0 otherwise, so if V is not isomorphic to W. So now let's prove this. So proof. We'll start with part 1. So it's possible to show that the image of the intertwiner T and the kernel of the intertwiner T are, actually I should write the image as a subspace of W and the kernel as a subspace of V are G invariant subspaces, i.e. subrepresentations. It's not too hard to show this. So what are we trying to show? Well, T is either an isomorphism or T equals 0. So we have, let's just remind ourselves that we have T going from V to W. So because of these two properties, we have either image of T equals W, and kernel of T equals 0, because the image and the kernel are both G invariant subspaces, and V and W are irreducible representations. We have that either image of T is equal to W or image of T is just 0. The same goes for kernel of T. Either kernel of T is V or kernel of T is 0, precisely because V is an irreducible representation. It can't have any smaller, non-trivial subrepresentations, so kernel of T must have that property. Same goes for image of T. But we can't have image of T equaling V and kernel of T equaling, image of T equaling W and kernel of T equaling V. We must have either image of T equaling W and kernel of T equaling 0, or image of T equaling 0 and kernel of T equaling V. But in this case, just draw an implication arrow. In this case, we have that T is an isomorphism, because it's an injection because the kernel is trivial, and it's a surjection because the image is the whole of the codomain. So it's a bijection, it's a bijective homomorphism, therefore it's an isomorphism. Or this implies that T equals 0 because the kernel is just the whole of the domain, so it must be the 0 map. So yeah, we've shown that part 1 holds. Now let's show part 2. Get rid of that dot there. Okay, so if V equals W, then T equals some constant times the identity map. Well, let's just write what we have. So if V equals W, then T goes from V to V, i.e. T is an endomorphism. We know that T is invertible, and well, our overlying field is, or underlying field is C over C. So by the fundamental theorem of algebra, there exists an eigenvalue of T. Right, now let's define a map. Well, actually, first, since we've just said that T has an eigenvalue, let's also define, or not define, let's just write the eigenvector associated with it. So let V in V be the eigenvector associated with the eigenvalue lambda. So T applied to V is equal to lambda times V. That's just what it means to be an eigenvector. Now define the map. T tilde is equal to T minus lambda times the identity map. Now, straight off the bat, we know that this is a G intertwiner because T is a G intertwiner. Lambda times the identity map is trivially a G intertwiner, and by linearity, this linear combination is also a G intertwiner. Now, let's apply T tilde to V. What is this? This is this linear combination applied to the vector V. So since this is a G intertwiner, it's a homomorphism, we have TV minus lambda identity of V applied to V, which is just this becomes lambda times V because V is an eigenvector of T with eigenvalue lambda, so this just becomes that. Let me highlight this quick. So this becomes this. Minus lambda times V, because this is just the identity map. Let me also highlight this. And this just equals 0. So V is in the kernel of T. But as we've just said, T is a G intertwiner. That's not very well written, but you get the idea. T is a G intertwiner. And as we've also said before, kernel of T tilde, which is a subset or subspace of V, is a subrepresentation. But again, V is irreducible. So by the same argument as before, we either have, let me just put a so there, so we either have a kernel of tilde is the whole of V, or the kernel of T is trivial, because this is because V is irreducible. Let me just highlight this point, because V is irreducible. But recall that, actually let me highlight this quick, recall that we have an element V in the kernel of T, so the kernel of T is non-trivial, so it must be equal to V. But then we know that if the kernel of some map is the whole of the domain, then the map must be trivial. So this implies that T is just the trivial map. But what was T? T was, what was it? It was, yes, T minus lambda times the identity map. But this equals 0. So we have T is equal to lambda times the identity map. So that's what we wanted to show for part 2. Now for part 3, we want to show that the dimension of the space of intertwiners between V and W is 1 if V and W are isomorphic, and 0 if they're not isomorphic. So let's show this. So part 3. What do we have to do? We have to show that the dimension of the space of G intertwiners is either 1 or 0. So let's start with the easier case. If V is not isomorphic to W, then by the first part, well, what do we have in the first part? We had T is either an isomorphism or T is 0. Well, T is not an isomorphism because V and W are not isomorphic, so by 1, T is 0, which means that the size of G intertwiners between V and W is just 0. So now, move this to the side a bit, now suppose that V is isomorphic to W. We want to show that there's only, well, the size of the G intertwiners between V and W, the size of the space of G intertwiners between V and W is just 1. So let's kind of assume the opposite and say that there are more than 1, so 2. So let T and S going from V to W be in Hom G V, so let them be G intertwiners. Now we look at part 1 again. Part 1 says either T is an isomorphism or T equals 0. Well, in this case we have that V V and W are isomorphic, so T and S are isomorphisms. So we can take the inverse of S and define a map. Define a map S inverse applied to T, going from V to V. This goes from V to V because T goes from V to W, and then S inverse goes from W to V, so the whole map goes from V to V. But now, if we look at part 2, what did we have in part 2? If V equals W, if the domain and codomain of our map are equal, then the map itself is equal to some constant times the identity map. Well, here we can see that our domain and codomain are equal, so we have, by part 2, just write part 2 here, that S inverse T is equal to lambda times the identity map for some lambda in the complex numbers. But then we can just bring the S to the other side, and we have that T equals lambda times S. But now we see, but now it follows that the dimension of the space of G intertwiners between V and W in this case is just equal to 1, because all we've done is scaled T by a constant.